Okay, so when last we talked, I was arguing that the energy transition for the first emitted photon was going to be 3.4 electron volts. Let me go over that again. Okay, what the problem tells us is that you have an electron chilling out here, it jumps down emitting a photon, it jumps down again emitting a 10.2 electron volt photons, and then no further photons are emitted. That means at the end, we kind of have to think about this backwards, right? At the end, it must be at the ground state. It just emitted 10.2 electron volt photon, which means before that it must have been at negative 3.4 electron volts, 10.2 electron volts higher. Then the first photon it must have emitted would have brought it down from 0 to negative 3.4 electron volts. So that photon must have been 3.4 electron volts, the difference, right? So the photon's kind of a subtraction thingy, right? When you go from 0 to negative 3.4 electron volts, you lose 3.4 electron volts of energy. It is subtracted, we could say, could we not? So that was exciting. The energy of the photon, great, 3.4 electron volts. The frequency, remember, E equals HF. We're going to use the electron volt second version of this and find the frequency is 8.2 times 10 to the 14 hertz. Muy exciting. Okay. Following diagram shows some of the energy levels, including how to draw arrows in the diagram. That's weird. You couldn't really do part A or B without really, or part B at least, without really doing C anyway. But just think about it. This is what's going on in the problem, right? And I've already drawn it in. We have a photon starting here, goes down to negative 3.4 electron volts, then goes down to negative 13.6 electron volts, right? Essentially, it goes down the ladder twice in two separate intervals, sending out those two photons. Okay? Yeah, let's look at one more just a little bit. Actually, we haven't really done D yet, have we? How embarrassing. So the atom's in the ground state when a 15 electron volt photon interacts with it. So it's here, and then it's get whacked with this huge 15 electron volt photon. All the photon's energy is transferred to the electron, freeing it from the atom. Determine the following: kinetic energy of the ejected electron. Remember, this is, you're in the quad. McCabe demands a certain amount just to get out, and then the rest you spend on tacos. His demand is called the work function, or the ionization energy. Well, how much energy does it take to expel this electron? Well, 13.6 electron volts. And with the remaining, it'll become kinetic energy. Okay? So if I only need 13.6 electron volts just to free myself, and I have 15 to spend, I'm going to have 15 minus 13.6, or 1.4 EVs of kinetic energy. The de Broglie wavelength, how do we get the wavelength if we know the energy? This is that kind of nightmare thing. We're going to get the energy, and we're going to use the energy to find the speed to find momentum to find wavelength. Here's what's annoying about that. We need to convert this energy into joules. It's not that annoying. 1.4 EV times 1.6 times 10 to the negative 19 joules per electron volt. Remember, that's what every electron volt has, will tell you. So now we got the energy in joules. Okay, I'll use the mass of the electron and the equation K equals 1/2 mv squared to find V. I get V is 7 times 10 to the 5 meters per second, and I use that V to find momentum. Same mass of the electron that I can look up on my equation sheet, 9.11 times 10 to the negative 31 kilograms. So I get 6.4 times 10 to the negative 25 kilogram meters per second. I want to find the de Broglie wavelength. Remember that lambda equals h over that p. So now I just divide h by that number, h in joule seconds, and I get 1.0 times 10 to the negative 9 meters. Whew. All right, so that's kind of silly. I mean, it's a lot of multiplying and dividing. It's not especially hard, but they like doing that. Again, to remind you, we took the kinetic energy, made it joules, found the speed, used that speed to find the momentum, used the momentum to find the lambda. Hey, I guess I'm not doing another problem for you. I apologize, but we'll talk about other stuff tomorrow. See you later.